Same point everywhere. So it's a set of exceptional points, in fact, can be infinite, subject to some structural properties of the set. So this is one of the first results which uses explicitly the structure of an infinite set of reals. And the requirement is that for some finite n number n in the nth-derived set is fine. All right, so such special sets of reals, which are referred as combinatorial sets of reals or extremal sets of reals, are very important, and they are part of the development of set theory and play an important role even in the civilization of mathematics, the appearance of ZFC up to date. So important combinatorial sets of reals, a Banach set which has the property that neither this set nor its complement contains a perfect set. Other important sets, meager sets, logically small sets, Lebesgue measure zero sets. And what we're going to see is we're going to study these sets from a set theoretic point of view, and we're going to see that these sets have certain infinite combinatorial structure, which allows us to tell more about their possible interdependence, if there is ZFC independence between sets, or the lack of such independence. All right, so the two directions that we're going to see in the next 50 minutes is, on one side, possible sizes of such sets. The very first cardinal characteristics of the real line is its size. How big is the real line? And this question is very closely connected to this work of counter trigonometric series representation of a function. And on the other side, how simple these special sets can be. Many of the sets that are of interest would be in fact the result of their existence of the axiom of choice, and in this sense, they're not constructible. So we'd like to know, well, how simple the definition can be given to such sets. So we'll study their projective. All right, I will start with some. I've chosen two objects, one which has its origin in algebra, and another object which has logical origin. So I would like to show you how these two objects interact and what is their importance for such a. All right, so let's look at something very simple. We look at functions from the natural numbers to the natural numbers. Right? And now we look at families of such functions which have the property that any two elements of the family are eventually different. So their graphs have only finitely many components. Right? Now we'll be particularly interested in maximal such sets, maximal under inversion. So far so good. So the minimal cardinality of such maximal different values stands for eventually different. All right. It's a very simple combinatorial object. What it has to do with bigger sets. See? Now let's add a little bit more structure on our infinite set of reals. Remember, we want to look at special sets of reals which has structure. So the structure is, let's look at such families of eventually different reals which have a group structure. So in particular, we're looking at permutations of numbers, subgroups of S infinity, the group or permutations of natural numbers, with the property that all the elements of the group are eventually different. Now, if for a moment you think, how can this be, and what does this mean for each member of the group, it essentially says that every non-identity element can have only finite X points. So such groups are, this is the reason such groups are called combinatorial, and we are interested in maximal combinatorial groups. All right. Now, these objects, combinatorial groups, our interest of which graphs in 1980s, in particular the electric magnet, what would they show? Well, they would show that if we have a countable combinatorial group, which is not maximal. Moreover, they would show that if we have a group such functions. And there is a graphic function which eventually dominates every member of the group. This group is not maximum. A result which can be seen as strengthening this last result appeared much later, around 2010. All right, sorry, I was there. Moreover, they also show that there is always maximum binary group, which is in projective correspondence with the real line. And now we come to a very difficult question in the area. Well, does this mean that every maximum binary group is of size continuum? It's a difficult question, and we'll see that the answer is no. But what else could Adelaide show? They could show, for example, they mentioned that if we have a finite group and there's a function which eventually dominates members of this group, yes.
Do any of these results use extra modules or not?
I do use the extra modules, yes.
All of them. Well,
this is the point. So yes, and it's important. So another result which can be seen in fact as strengthening with this result of Adelaide and Neumann is that which recent result Brandish, Venus, and Jan, they would show that if every set of cardinality alpha is logically small as mirror, then there are no maximum binary groups. So in terms of combinatorial cardinal characteristics, this first result, like says that the volume number is basically G. This can be defined as the least cardinality of the non-neighbor set. And the result of Brandish, Venus, and Jan says that the least cardinality size of a neighbor set, of a non-neighbor set. All right. So, to what extent the presence of a group structure indicates a different unit? If we have a group structure, then theoretically we have a fewer number of finite groups than we have eventually different elements, right? Because every finite group is eventually different. And so if we take a minimum over a large object, we should have a smaller number. That's theoretically very good, but we are far from actually having this result. In fact, an interesting question, and I promise very many of the question is, what can we say about the minimum cardinality of a maximum eventually different entity, minimum cardinality of a maximum binary group? I just gave a very affordable conjecture that probably AE is answering for AG. In fact, it's very much open. We not only we do not have a zealousy probe or relation between these two cardinals in difference with E and the first the migrainium, but in fact we even don't know it is open consistent. So infinities are distant. So however, the investigation of this combinatorial sets is very natural. So what we see is some indirect differences between the uniformity of the migrainium between this cardinal invariants A, E, G, and some other combinatorial objects. So yes.
Question. So the continuum hypothesis doesn't imply that they are equal.
The hypothesis is planetary.
So consistency.
But we don't know. Are we to accept the continuum hypothesis?
I mean, it is consistent.
Well, they're consistently equal, but all right.
Yeah,
we don't know if it's consistently different.
Oh,
we do not know if it's consistently different.
Okay, sorry. Yes. Yeah. Okay.
All right. So So both AE and AG can be seen as a relative of a simple cardinal invariant, which is the almost disjoint. So we forget about given being a function requires structure set. Now we forget about all kinds of structure. We just look at infinite families of infinite sets of numbers, whose elements are pairwise disjoint and are maximal under inclusion. Then the almost disjoint number can be defined as the minimum regularity of infinite maximal almost disjoint pair. So to what extent? So all of these binary groups, different families, their graphs are almost disjoint. So to what extent they represent different affinities, different properties of the real line? Well, a first distinction is the relation of this object to a nonlinear sets, informative to be given. Now, on one side, we have that the minimum cardinality of a nonlinear of binary group is never smaller than the minimum cardinality of a nonlinear set. On the other hand, we have that the minimum cardinality of a nonlinear set is a cardinal, which is independent from the almost disjoint. There is no ZFC relation. So consistently, the almost disjoint number is smaller than the uniformity of the figure here. But also, it is consistent that so consistently they are maximum almost disjoint family. And consistently, uniformity of the middle radial is smaller than the almost disjoint, which is a very interesting result. Another point of distinction between these combinatorial objects comes from their projective complexity. On one side, there are no analytic, it's a celebrated result of Adrian Matthijs. There are no analytic maximum disjoint families, but they are rare maximum binary groups and maximum eventually different. From point of view of their projective complexity, these objects are very different. All right, so now we have already two main directions that we want to discuss. On one side, a study of the possible sizes of such combinatorial sets of pairs, which do serve as some kind of measurement of the properties of the real line beyond their own value. We can speak about binary groups, nonlinear sets, and the list is much longer. And on the other hand, the other direction to find out is the projective complexity of such sets of pairs. All right. So as we're going to see, and this is pointed out, what are these sets? What are their possible values? What are their projective complexity? It very much depends on the auxiliary model that we either create or we are in and the concepts. So how can you generate, going back to the question of the leg diamond from the 80s, is every maximum combinatory group? Just another characterization of the continuum. Is every maximum binary group the size of the continuum? And the answer is no. So one can Ijan essentially use the idea of Solovay for generating for what is almost disjoint coding to generate a maximum binary group of arbitrary, almost arbitrary. So we start with a binary group, say count model, and we add one new generator at a time. We want to add a single new real which extends the given group and has some additional properties. These additional properties are very important. So this is a forcing construction. However, I want to give you the idea of this construction. One can see the idea of the construction even without the forcing terminology. So essentially, we want to have a real group. And we want to join a real, which has the property that when we add this real to our group, we still have a binary. And this property is sufficient to produce large binary groups. What we cannot produce is semantic, and this becomes a very serious point for other chats. And the second property is that if we have a real binary rotation, which is not G, and is an hypothetical, then we want that this is our real that we are constructing using finite approximations. It's going to prevent any such intruder into enlarging our group to yet a larger maximum finite group. So this would eventually, in a course of construction, guarantee mathematics, but one can think of really recursively joining one generator after the other. All right, so how far is this bringing us? Well, this is giving us comparatively much. It essentially said that whenever we have two regular uncountable cardinals, or at least cardinals uncountable cardinality, then we can construct a model in which the continuum is lambda and the minimal cardinality of maximum finite group is equal to kappa. All right. Now, this approach, however, leaves some interesting open questions. Is it true that there is a maximum finite group cardinality at omega? Remember that the continuum, by the results of Colloquium, can be any but cardinal cardinality result of So in particular, the continuum cannot be equal to. What about this minimal size maximum finite groups? Can there be is there a model? Is it possible that the size is equal to 1? And this approach for joining real time is not going to give us the answer. We need a different method. So this different method is interestingly enough, it's essentially can be briefly described as following. So we have an arbitrary index set. Essentially, we would like our index set to be and we would like simultaneously for every element in this index set to associate a binary representation in such a way that all these binary representations together generate a maximum binary. Well, this can be done. And how it works, we work with finite approximations. We choose finitely many elements of our index set. And with each of them, we look at the finite approximation, finite injective function, which is intended to be seen as an approximation of the ith permutation we aim to construct. And we work with all these approximations. We generate the partial order, with partial order on this finite approximations, and this allows us eventually to generate with these finite approximations by gluing them together in an appropriate way, then forcing a maximum finite group of size omega. All right, having a maximum finite group of size omega is the first step of obtaining a model in which this minimal cardinalities need more. We need to prevent any other smaller size as being realized as a maximum finite group. And this can be done, but this is a very difficult, in fact, this builds on the groundbreaking work of Scheller on the consistency of the dominating number being more than competition. So if you don't know what it is, it's fine. But this is an extremely interesting course of construction known as template. All right. So yes, no is trying to say we can consistent. However, this simple idea of approximating simultaneously this larger combinatorial object with finite conditions. It's not always work, and leaves some open and very difficult, interesting questions. One of those is last item on the slide regarding the independence number. I will go over this hopefully. The last part of my talk. What is interesting is that, well, only recently we were able to show that such an independent moment you can just think of it as a special item in Veros and Rios of cardinality of omega can consistently exist. But we're still not able to exclude this more difficult task of excluding smaller values, smaller cardinals as being realized as independent entities. All right, going back to the second line, the line projective complexity. How did the real maximum planetary group how it's essentially obtained? It wasn't an answer. It wasn't an immediate discovery. We just saw it. Well, in fact, it took a lot of little steps until this object was created. So the first were Xu and Zhang, who observed that in the constructible universe, one can construct a maximum planetary group which has a coordinated set generators. Now, in the constructible universe, if you're familiar with it, there is a sigma 1 to low order derivatives. So using this low order derivatives, I can use sigma 1 to define limits. So decreasing the number of quantifiers, simplifying the definition, takes an actual work. All right, we have the result of Sugal and Tijan. Bart Castermans, in fact, show that in the constructible universe, not only there is a finite group with a coordinated set of generators, but the whole group can be analytic. And in conversations with Castermans, he was really, really annoyed by the fact that at the time he was looking at these questions, there was no clue. He was certain that there is such an object. It wasn't clear. It wasn't clear to him or to anyone else how to obtain such an object. And eventually, the paper, well, I think the result is around 4 years old. The paper is almost to be published very soon. Because there is a grammars group. Okay. So, summation. This real object is of size continuum. The maximum planetary groups in constructible universe with FCH, they're also continuum. Well, but we spend so much effort answering the question of the Lake and Neumann that consistently there is a maximum planetary group of size smaller than what about projective subjects. And it is only recently that this object becomes even being addressed. Our focus seems at this point has been entirely concentrated into providing such good projective witnesses for the simplest case of planetary size continuum, which always exists anyway. All right. So, well, trying to obtain planetary groups which have nice definition in models of large continuum, let us gradually to a combinatorial object which is of interest by itself. I'm going to describe it and give you the definition shortly. But it's really a gradual process. So, as a first step, we would show that in the constructible universe, there is a maximum planetary group, which is quantitative, which remains maximal after we add very many quantities. Now, the combinatorics of the partial order, so when you can think of it, if you don't know forcing, you can think of it as some additional requirements we want our maximum planetary group to satisfy additional combinatorial requirements. But these requirements are very tightly connected to the partial order, the specific partial order, which in this case is just from point of view of the properties of the real line and combinatorial characteristics, you can think that various forcings provide various properties. So we could obtain this result, which is a serious result. It's published in the journal Logic. But there's so many other questions left over. What if instead we wanted not to add countervails, which had a certain effect on the whole real line, but we wanted to add sex rings? Well, our construction is so tight, so specific for found forcing, it did not work. So eventually, 2 or 3 years later, we were able to show that in fact, in constructive universe, there is a maximal eventually different family which has a nice definition and remains maximal after we increase the continuum, which is the sex rings. So we had to need further combinatorial properties, and in a certain sense, we designed a very specific maximum finite which met these requirements. But the list of forcing notions is far from being exhausted. I put two forcing notions: con forcing and sex forcing. These are the first that everyone should know. That's but the list is much longer. So are we really going every time we face partial order that has the potential of preserving the finite group have to create such a more difficult object? So well, I'm not sure if we stumbled upon the notion, but in developing these various combinatorial objects, we essentially found something interesting. We found eventually different family, which is combinatorially very robust. It survives various partial orders, so it can coexist with various other properties of reals. Moreover, this special maximum eventually different family, which we constructed, is also different than the maximal eventually different family of Hopkins and Chalat. And you see exactly how it's different. So now we produced, thanks to some forcing combinatorics, an interesting combinatorial object which exists under CH. It exists under the pseudo intersection number continuum. So we found something new and interesting. So what is this? Give you an idea of what the subject is. Well, when we, of course, every function is a set of pairs. So we want to think of our functions from the natural numbers to the natural numbers as points in the Cartesian product of the natural numbers themselves. And in particular, we'll be looking at trees. So these are just sets, finite sequences of natural numbers, which have a tree structure. And you say that family of functions almost covers a tree if all but finitely points on the tree are in fact belong to the graph of one of the functions. All right, so nothing interesting except for the moment. I just change the perspective, take the functions as points in the plane. All right, now we are going to look at the following interesting collection of objects. We refer to this as a trivial of a set of functions from the natural numbers to the natural numbers. These are all trees which have the property that there is a node in the tree such that the whole cone of the tree, all the nodes which extend this given node, is eventually covered by a finite set of functions from our family. And we say that the tree T is positive with respect to a family of reals, functions, if no node of the tree, this never happened, if no cone of this tree is almost covered by a finite set of functions from the given family. Right? That's a combinatorial property. We don't know much about anything in order to give this definition. So, what is this type eventually different family? Well, if we have a tree of such finite sequences of natural numbers, we say that a real G densely diagonalizes the tree if for every node in the tree there is a branch to the tree which is infinitely often equal to this G. Finally, the definition strengthening similarity for eventually different families. An eventually different family is said to be tight if whenever we have countable family of trees which are positive with respect to the ideal, which are positive with respect to the family of functions, which means that no cone of any of those trees is covered by finitely many members of the function of the family. There is a single function in the set E, which densely diagonalizes all members of all these trees, all these potential intruders. So this, the name diagonalization is, it has something to do with this technique which I showed you at the beginning of Ijam's method of generating these. This is becoming technical. So why are tight families interesting? Well, they're maximal. They exist under CH, or over what it's also true they exist under certain number equal to the continuum. They are never analytic. So this can be seen as a strong distinction with the real maximum eventually different family of coverage. All right, so that's great. We have this combinatorial object, and now how I know that this combinatorial is strong? Well, it is in fact remains maximal by after forcing with a much longer list of forcing notions. So in particular, we had that very many possible cardinal characteristic constellations are consistent with the existence of such special maximum eventually different family, which on top of everything can have a nice definition. So this is the strong combinatorial object that we were able to construct. All right, so how about projective complexity? Going back to the line of discussion, so all this development came from the fact that we were looking for a nicely definable maximum eventually different family in a model of large continuum. So we found such. So what about finding maximum eventually different families, which are of any other different size of M1 and 15? So in particular, we'll be looking at finitary group or finitary groups or eventually different families, which have cardinalities strictly between α1 and C. And we would like to have a combinatorial object which has optimal projective complexity. In other words, there is no witness to this cardinality whose definition of complexity is strictly below this is the object we're trying to construct in the projective hierarchy. All right, so so everything that has been done very recently, it's not answering the question. We can have a maximum finitary group of a smaller size, but can it be of optimal projective complexity? And what is this optimal projective complexity? Well, it is in fact sigma 1, 2. It turns out that the least projective complexity is pi over 2. And after significant work, we can get an intermediate, a witness to an intermediate value in the spectrum of moments, which is as this optimal projective complexity. All right. So this is true for maximal eventually, maximal, almost joint families, maximal finitary groups. But where we are, where is this line of investigation? Where has it brought us? So on one side, we can have a model in which the spectrum, their maximum eventually different families, only two sizes, α1 and this is the con. So in the con model, moreover, we have realm finite group, maximum eventually different. Okay? size continuum. So optimal witness. And we work very hard to produce a 5-on-1 object of size one, or after 5. So we have a model in which every cardinal is witnessed by our object optimal projective text. So we can speak in a certain sense an expanded notion in the spectrum of optimal spectrum. Right? All right. So what if we want to? What this is very specific for unforeseen. We can work very, very hard and provide an optimal spectrum for intermediate value or all possible intermediate values. We always have the broad binary group or maximum dimension different family. What we do not have is third possible. So it seems that in all our attempts, all the work that has been done, we can meet at most 2 out of 3 challenges. And all of our techniques and everything we've tried so far, that's where we are. I'm just pointing, I promise there are many other questions. So the situation with combinatorial groups is very similar. All right, so second type of objects I want to discuss in the next 8 minutes are independent families. All right, independent families have been around for very many years. They are already known to Hausdorff, Fichten, Skankovic, and I'll give some classical examples of such families. All right, but what is an independent family? Let's look at a very clear definition. We look at families of infinite subsets of numbers which have the following property. Family A, whenever I took two disjoint finite subfamilies, A0 and A1, I associate with those two subfamilies set which I obtained by intersecting the members of the first family with the complements of the members of the second. So this is this here, and I refer to this as a Boolean combination. Right, so we say that an independent family is independent if every such Boolean combination is an infinite set. And we'll be interested in maximum independent families, maximum inclusion, and particular interest is the minimal cardinality of such maximum. All right, so a convenient way to describe Boolean combinations is just to look at finite function from the set into 0, 1, and just encode the first family A0 with a preimage of 0, the second family as preimage of 1. This is a convenient way to speak about these Boolean combinations. And if we have H prime, a function with larger domain which extends given function H, then we say that the Boolean combination associated to H prime strengthens the Boolean combination associated to the function H. Far so good. So a moment of consideration shows that if we have a countable family with this property, we can just enumerate all the Boolean combinations countably many and find the set reduction, construct a set which is independent over the family. All right, and there is always an independent family of size 15. This is an example of which is following. Now we look at the collection of all finite subsets of the rationals, which all right, so finite subsets of the rational, and with every real, we look at all those finite subsets of the rationals which have the property that below this real R, they have at most an even number of elements. Right, so this is clearly an infinite set, and moreover, the density of the rational numbers guarantees that the collection of all these sets AR is independent. Okay? And this is an independent family of size continuum. Using the axiom of choice, I can extend it to a maximum. There is always a maximum independent family of size. All right. So, well, is this just another characterization of the continuum? In other words, is it consistent that there is a maximum independent family which is cardinality strictly smaller than than the continuum? And the answer is yes, one can obtain such a model, one can force such family using a technique very similar to this technique of the joining one generator at a time. Again, the tasks split into essentially extending an object and somehow preventing something from happening. This preventing something to happen is probably a more difficult task. It can be achieved, right? So essentially one can push the technique yet once again to obtain a consistent minimal cardinality family history where the values are regular. So alpha the hidden value for the continuum still beyond our reach. The snake is not allowing us to achieve it. So we needed to do something different. And eventually we were able to construct to force the existence of a maximum independent family size omega. It is not as simple as achieving it in this very simple construction, which we approximate the generic object by conditions. But we would nevertheless obtain the existence of such an object. What we could not obtain, what's still an interesting problem, is it consistent that the minimal cardinality of an maximum independent family is equal? We still don't know. All right, so all right, so I will make all right, so on one side we have this analogy of the forcing notion, which allowed us to add a maximum planetary of arbitrary size. We can add a maximum independent family of arbitrary size. We cannot guarantee that there is no smaller object of this size than an interesting phenomenon which gradually occurred, which we gradually understand, is that just looking at such forcing combinatorials, we can construct a very special maximum independent family, which has a number of additional properties, which is indestructible by a large class of forcing notions. And this so this is very interesting. All these constructions are, in a certain sense, that there is similarity, but this similarity is not that visible. So what turns out is that similar to tight maximum eventually family, there is notion of strengthening maximality for this independent, this selective, which are robust under various forcing notions. And what is a very recent result, 2023, it's almost done writing it, is that such combinatorial objects not only exist under the continuum hypothesis, but again, under the hypothesis that the pseudo intersection under is equal to continuum lies in existence of such very strong all right. So how far and how well we understand the projective complexity of independent families? No, we know that consistently, we know that they're analytic one, but we know that in a constructible universe we can construct co-analytic selective independent families if their existence is consistent with the continuum being large. That's as far as we know nothing more about projective complexity of independent families with its size. And if we could meet 2 out of 3 challenges for maximum eventually different families, for independent families, we can meet 1 out of 3. So the research is not as far to the boundary of no, not as far as our understanding of constraint elements. All right, and since I promised to tell you, right, there is interesting stuff happening in the area. And here are some of the most popular combinatorial cardinal characteristics. So how is a good way to think about this? Here is the reals, the size of the real line. Here is one one. Here is a celebrated result. And here is a lot of other characters that I spoke about. The almost jointness number, the independence number. I did not here in this diagram do not appear. AG and AE is not like that. So we can think of these nodes whenever we have a line, we have a Z of sigma going forward. If we have a line, well, many cases it means independence. Diagram is not complete. An open question is, are those two cardinals independent, A and I? And this is another interesting question. Is the diagram complete? No. And as very recently, we found another very natural combinatorial object, which is just right here above the so new things to here. Now, where if I'm to say what seems to be a natural tendency, where all these questions bring us to, for a long time. Well, 20 years ago when it's PhD, the question is, if you have two combinatorial objects, can you separate them? Is there a Z-C relation between them, or can they be different? And are they compatible? So in terms of this diagram, it just says, are those two values independent? Now, there has been significant development over the past 20 years in terms of understanding the properties of the real line. And now the questions which are more natural, which really capture our attention is, choose any finite number of elements of this diagram, more than two. And pick a diagram of constellation which is not forbidden by ZFC, it's not forbidden by these relations that we know of. Can you realize it in a possible extension? Is it consistent? And almost any finite number of cardinals that you will choose will give you an open question. And moreover, they will give you everything. But that's where it is. Thank you.
Is there maybe one question you would point out for the grad student? All of the many possibilities.
I think that it's a question which I would certainly describe as difficult is the consistency of the dependency groups of the decisions. This is the simple question. Well, this would be a question regarding this continuity properties. So we take the cardinal, which is between one. So divide maximum mu, which is optimal equivalence of projective. This is a difficult question, but not very. So this one, I think I can find it. I bet that if you work hard, you'll find a solution. The first one, please find a solution. Yes.
So, question, do these maximal combinatorial groups have some notable group theoretic properties? I don't know, are they simple? Can one say something about countable index subgroups?
Well, I'm not as familiar with their study from Frank. What I can say though is what is for me very everything that we can provide, everything that we can generate is really generated groups. We cannot do anything seems to be somehow unnatural. So they're free groups, yes.
Okay, there is no theorem that says they have to be, but
No,
examples.
we don't. There shouldn't. Yes, there is no theorem that says that they should be, but that's all that we can do. Which says that it's much more like to do.
Actually, I'm a drop confused about that. I mean, didn't you start off by, you just start off with some group, right? And then you begin adding all the things in. So if I started off with some silly group that interchanged the odd and even numbers, right? It was a group of order 2. So then you end up, the group that I'll end up with won't be a free group, they'll still have an element of order 2 in it.
Yeah, no, that's a good point. The generators that we can add are somehow
Hard proof, but,
yeah.
but you can start off with the seed, your own choice.
You can start with this any.
You can start with any countable group. I think of
Yes.
it as the K-league, and then let it act on itself. And then you have, some such group that will contain an arbitrary countable. So it's a one-free group. Yeah, right. Yeah. Yeah, but the question about whether it's a simple group or not.
Yeah.
So regarding these questions of, given a strictly greater than 2 number of cardinalities and relative, what are some results that we have? So are there 3 cardinalities that by looking at the diagram, I might suspect it's consistent, they're in such and such way, but actually no, by some surprising.
This is crunching.
Okay, so
Yeah, of course, there are examples. We know of certain constellations which can be realized. Maybe you have heard about the celebrated result of Sacco Shella, Martin Rothstern, and Kellner about the Kishon maximum. So the invariant measure, the ideals, sigma ideals of measure of vector 0 sets and bigger sets. One can characterize them in terms of 4 cardinal characteristics. Each of them together we get 8 characteristics. They're very well studied. In fact, any possible ZFC relation, we have a complete diagram. So there are 23 possible constellations in which the values of this measuring category take values alpha and alpha 2, and they all have been achieved in difference with this diagram. So this result of Sacco Shella, Martin Rothstern, Kellner says that, well, there is 8 characteristics. In fact, there is a constellation in which all these 8 characteristics take different values. However, this is called the Kishon maximum. So this is an example of a constellation which would have these 8 values. However, there is a large number of admissible characteristic constellations, I think around 63, maybe that off. And only one of those, or 2 or 3, have been realized. So there is a large number of explorers. This is the frontier. We want to know where did the relation between more of those characteristics becomes problematic.
So let's thank our speaker again.